Hi and welcome to Specialist Maths Unit 1, Topic 1, Video 8, where we're going to start looking at combinations. Of course, you'll recognise that this whole topic is called combinatorics, or maybe combinations and permutations. We've covered the permutations, and we're going to start looking at combinations. So here are some learning goals for the next 4 or 5 videos, and some success criteria for you to use. Of course, my reference material for the textbook that we use. So we know that a permutation is an arrangement where order matters. So we calculate permutations on placings in a race, for example, or positions around a table where order might matter, or something like that. A combination is an arrangement where order does not matter. So if, for example, there are 20 students in your class and you're hoping to be selected for a cricket team, well, perhaps you just need to be in that top 11. And it doesn't matter whether you are picked first or whether you're picked 11th, you're still in the team. And so order doesn't matter about that selection. And so here we have an example very quickly where we're talking about the selection of 2 college captains versus the selection of a captain and a vice captain. So 2 college captains, that's a combination, because in this case, order doesn't matter. You get selected first or second, you're still one of the college captains. Whereas a captain and vice captain is a permutation because order does matter. And so you're being selected. If you get selected first, then you're the captain. Second, you're the vice captain, or whatever the generalization is there. So this is the slight difference, and it leads to some mathematical difference in commutations and permutations. And I encourage you, if you want to do really well in this subject and in exams to do with this, you'll have a really deep understanding of that difference, which I'll try and get across in these videos. But of course, you might need to read a bit more widely. So first of all, generalizing a combination. If we choose R objects from N, where order doesn't matter, well, then this is called NCR. And that's what we're referring to. So NCR is N choose R. Now, the C is not really for choose, it's for combinations. It's a bit like the P is not for pick, it's for permutation, but it is a nice way of saying it. N choose R, and it's N factorial over R factorial, N minus R factorial. Now you'll notice here that this is the permutation one. And then you'll see I've done some work over here, so I'll just highlight as I go through. I've just said NCR is equal to this stuff, which is equal to this divided by R factorial, which is equal to NPR divided by R factorial. So the combination is the permutation, but we divide the number of options by R factorial to indicate that there are R factorial ways that that selected group could be organized. But we're saying order doesn't matter. So we're reducing that the number of permutations by R factorial to recognize it doesn't actually matter when you got chosen. So that's the link, the connection there between permutations and combinations. So let's have a look at a quick example. In example 1, how many ways can a 3-person table tennis team be chosen from 5 players? So in this case, we're talking about 5C3, because it doesn't matter whether you get picked first, second, or third. And 5C3 is 5 factorial over 3 factorial, that's R factorial, times 2 factorial, that's N minus R factorial. And that's equal to 5 times 4 times 3 factorial over 3 factorial times 2 times 1. I saved myself a bit of time by recognising that I've got this tail that I can cancel out. So I picked the highest factorial in the denominator, and I use that as a tail for my numerator factorial. And I'm left with 2 times 1. The 2 and the 4 cancel out to give 2, and so this is 10. So 5C3, there are 10 ways of picking 3 people from 5 players. Okay, so now let's have a look at this in a little bit more detail, a little bit more theoretically. Firstly, note 1, NCR is equal to NC N minus R. So this is a bit of a tricky thing to look at now, but what this is saying is that if I select, let's say numerically, I select 7 from 10, this is the same as selecting 3 from 10. It's a complement situation. So we're saying 10C3 is the same as 10C7. Now let's go up to our example here and talk about that a little bit. So when we're picking 3 from 5, this is what that looked like. I've got 5 students and I'm selecting 3 of them. So I said, well, there's 5 ways of picking the first, 4 ways of picking the second, and 3 ways of picking the third. But then we had to divide by 3 factorial because it didn't matter which way they were organised. But it also meant there were 2 that didn't get picked, these 2 here. So the flip side of that is we could say, well, how many ways could you not pick 2 people? And that would be 5C2. So 5C2 would represent the number of ways of choosing 2 people to not go. And then, of course, you'd have 3 people left over, and they're the ones going. So these have to be the same. We get that direct reciprocal or complementary arrangement where this must be 10 and this is 10 because there's the same number of ways of picking the 3 people to go as there are picking the 2 people not to go. And 3 plus 2 is 5. So that's where that comes from. But I've asked, can you show this algebraically? So let's have a quick look at this. I know NCR is equal to n factorial over r factorial n minus r factorial. And the right-hand side is NCn minus r, which is equal to n factorial over n minus r factorial times by n minus r in brackets factorial. Has to be tricky, and I can see that this little fraction bar needs to be extended. And now I can simplify this bracket because I can already see that that bracket is equivalent to this bracket. So when I simplify that, what happens? And I get this equal to n factorial over n minus r factorial n minus n plus r factorial, which of course is n factorial over n minus r factorial r factorial. And if I zoom in here, you can see that this is just a reordered version of that. And so this is equal to NCR as required. So we have that reciprocal relationship, really important one to recognise. So that's note 1. And it's definitely worth making this note somewhere in your book and referring to it where you need to. Note 2 is that NCR equals n factorial over r factorial n minus r factorial can be written in a few different ways. So NCR is also sometimes, this is not really that common, sometimes written as NCR like that. Sometimes written as NR in double brackets. This is more common. And it's also sometimes written as NCR like that. So there's a variety of ways you could see it. This is the way that I like because that's what I grew up with and it's just what I'm used to. And this is a really common way as well. And the other 2 might pop up. So just be prepared for that and look for it. So let's do another couple of examples before we finish this video. First, I want to calculate 6C2 without your calculator. And we've kind of done a question like this already in example 1. So 6C2 is equal to 6 factorial over 2 factorial, 4 factorial. So we've got those complements. It's n factorial over r factorial times n minus r factorial. So the 2 plus 4 makes 6. And I'm going to work with that tail now on my non-calculator question. 6 times 5 all the way down to the biggest factorial on the bottom. And then 2 factorial times 4 factorial there. They cancel out. I get 30 over 2, which is equal to 15. So there's my 6C2 simplified without a calculator. And then I've got my second question here, which is calculate n plus 1 c n minus 1. So this is quite algebraic, but again, we can do this fairly easily if we just follow the rules. Okay, so n plus 1 c n minus 1 is equal to n plus 1 factorial. So this is my n in the rule, this is my r, over n minus 1 factorial times by n plus 1 minus n minus 1 factorial. And that's going to be equal to n plus 1 factorial over n minus 1 factorial. And then n plus 1, well, I'll write it all out, n plus 1 minus n plus 1 factorial, which is equal to n plus 1 factorial over n minus 1 factorial. And then the n's cancel out here, so I get 2 factorial. So that's quite nice. And now I'm going to carry on simplifying. I'm going to use the same rule as we had before, where I bring the n plus 1 factorial down to the highest factorial in the denominator. So this becomes n plus 1 times the one below that, which is n, times the one below that, which is n minus 1, and I'll just factorial that over n minus 1 factorial times by 2 times 1, because that's 2 factorial, and this cancels with this, leaving us n times n plus 1 over 2. And it's always really nice if we can simplify it and remove the factorials. Once we remove the factorials, life's a bit easier, and you could write that in lots of different ways. So maybe a half n squared plus n, or whatever variety of ways, although we know that keeping it factorized is always a good idea. So that's example 2. We're going to have a look at one more example now, example 3, and then we'll be finished this video. A chess team with 6 players is to be chosen from 10 students. How many such teams are there? So this is 10 choose 6. And 10 choose 6 is 10 factorial over 6 factorial 4 factorial. But let's say there's no indication here we can't use a calculator. So let's assume that maybe we're in a calculator exam and 10C6, I can put in my calculator and I get 210. So I'll be taking the time now to make sure that you review your understanding of this video, do some questions on it, but also maybe take the time to go and check that you can actually use the calculator for these style of questions. All the best.